Hello, I'm Terry, and in the last video, we talked about this weak acid-base reaction, and we showed, we just determined which compound acted as an acid and which one acted as a base, and we determined that the reaction favors the reactants because of the strongest acid. But you could also look at this in terms of which one's the strongest base as well. It's not all about the acid. You can look at the base too. We have two bases here. And which one of these are the strongest base? And the stronger base is going to be more reactive. It'll almost overpower the other one and push the equilibrium to the other way. So I'll show you that. So if we look at the base, we want to compare which base is stronger. And just like acids, in order to know the strength of the acid, we use Ka values. In order to determine the strength of a base and relative strengths of bases, we use Kb values. Now if we go to our table here, there it is. And this is from the last video as well. Often you're not given Kb's. Often you're only given Ka's. So in order to calculate or determine what the Kb values is, we can convert them to Kb's. Now there's a shortcut, but I'm going to show you the kind of the full way without any kind of shortcut right off the bat. It's nice to understand what's going on in order to apply the shortcut, because if something changes on the exam, your prof or teacher changes things a little bit just to check your understanding, and you can't use the shortcut, then you're in trouble. So I'll show you the kind of the way without kind of any shortcut. So if we look at our bases, here's our bases here, and we need F minus. Let's do another color. Let's make it blue. B for base. B for blue and base. So here's a base here, the F minus, it's the conjugate base. And then the other one is, what was it? So this is, we were comparing this as an acid, this HSO3 minus. But this is it acting as an acid here, the Ka value for HSO3 minus. We want to know what HSO3 minus is as a base. So we need to see it on this side. I think it's a little higher up. Yeah, here it is. So this is it. It is the conjugate base of H2SO3. Okay, so in order to know the Kb, we find out what the Ka is of the conjugate acid. This is the conjugate acid, and this is the Ka. So the Ka of H2SO3 is 1.3 times 10 to the negative 3. So Ka of H2SO3 equals, I gotta look at that again, 1.3 times 10 to the negative 2. 1.3 times 10 to the negative 2. And for F minus, I think it was 6.6 for the Ka for the conjugate base. Here it is. Yeah, so the Ka for HF is 6.6 times 10 to the negative 4. Ka of HF equals 6.6 times 10 to the negative 4. And to get the Kb value, which is the equilibrium constant for it acting as a base in water, we use this nifty equation, which is not too hard to derive, but Ka times Kb equals Kw. And at 25 degrees Celsius, Kw is very close to 10 to the negative 14. It's pretty much that, within 3 sig figs anyways. So Kb of the conjugate base of this, which is HSO3 minus, it's going to equal, so we got to solve for Kb. Kb equals 10 to the negative 14 divided by Ka. So Kb for HSO3 is 10 to the negative 14 divided by 1.3 times 10 to the negative 2. I'll plug that in my calculator here. Negative 14 divided by 1.3 exponent negative 2. This is 7. I'll put it down below here. 7.69 times 10 to the negative 13. And here, if we do the same thing, Kb, this would be of F minus now. Kb of F minus is 10 to the negative 14 divided by 6.6 times 10 to the negative 4, which is 10 to the power of negative 14 divided by 6.6 exponent negative 4, 1.52 sig figs times 10 to the negative 11. Okay, so we have, this is the Kb for this bisulfite for this one, and this is the Kb for F minus. Which one is larger? Well, this is a bigger number. See, the exponent is lower, so it's closer to, it's the larger number, essentially. So this is larger Kb. So that Kb is larger. So this is the F minus is the strongest base compared to this one here, the HSO3 minus. So in terms of which way the equilibrium will lie, think of these bases as competing against each other. And a base is a proton acceptor. So which one can accept a proton to a better degree? Think of like a basketball. If you're playing basketball and you're trying to steal a basketball from somebody, the bigger person with the stronger muscles might be the better person that can grab the basketball a lot better. So they'll win most of the time when they're grabbing that basketball. This is the stronger base, so it's going to win most of the time when it competes against this base for accepting a proton. So because of that, the equation will lie to the left here. Yeah. Another way you could think of this as the strongest acid. The stronger the acid, the weaker the conjugate base. So because this is the strongest acid, then it's going to produce a weaker conjugate base than this acid. A weak acid will produce a stronger conjugate base. So the strongest acid produces the weakest conjugate base. So just by that, without any calculations, this base has to be weaker than this one here. So the reaction lies to the left.